Hello everyone, my name is Stu Adler. Welcome back to Introductory Lectures in Thermodynamics. In the last episode, I introduced the idea of chemical potential and the general conditions of equilibrium involving multi-component mixtures. I then went through several examples of equilibrium in binary mixtures, where we assumed either an ideal mixture or dilute solution. This led to a number of familiar equilibrium models, including Raoult's law, Henry's law, and colligative properties, such as freezing point depression. However, what happens when mixtures are not ideal? Although non-ideal interactions in liquids is something you'll explore in greater depth in Chemi 326, I'd like to spend one episode introducing you to some of the key ideas and show you one simple model for unfavorable interactions in liquids that helps explain some of the phenomena we explored earlier in the quarter. This behavior includes liquid-liquid phase separation and azeotropic mixtures. As a working example, let's return to the world's most famous Pokemon, Pikachu. Of course, what we're really talking about here is the TX diagram for mixtures of methanol and hexane. Let's try to explain some of the features of this diagram. Before continuing, a brief caveat. The diagram shown here is not actual data, but is itself a product of a model. In this case, the Uniquac activity coefficient model, which uses a quasi-chemical approach to modeling the energetic and entropic interactions among molecules in a mixture. For now, let's try to understand what's going on at a more basic level, using something called the Margules Equation, which treats non-ideal interactions in a mixture using a single parameter. First, consider the intermolecular forces that are likely to be dominating this mixture. In pure hexane liquid, which is a nonpolar alkane, intermolecular forces are due entirely to London dispersion forces. In contrast, in methanol, which is a much smaller but polar molecule, intermolecular forces are dominated by hydrogen bonding and direct dipole interactions. Although induced dipole and London dispersion forces between hexane and methanol are significant in a mixture, they're not as strong as the attractive forces in the pure phases. If this effect is strong enough, we might expect the liquid to be unstable as a single phase, and/or for the boiling point to be much lower than for the pure liquids. That's exactly what the phase diagram seems to show. Thus our goal is to come up with a simple model that can capture these effects quantitatively. As a basis, consider first an ideal mixture of two liquids A and B. Recall that for an ideal mixture, the total enthalpy and entropy are simple sums of the enthalpies and entropies of the species prior to mixing, with an additional contribution to the entropy caused by random mixing. Last time we took partial derivatives of H and S to get the chemical potential in the mixture. But another way to think about this is to first add H minus Ts to get G, and then divide by N so as to look at the overall molar Gibbs free energy of the mixture. As you can see, molar G of the ideal mixture is simply a mole fraction weighted average of Ga and Gb, which are the molar Gibbs free energies of pure A and pure B prior to mixing, plus RT times the sum of X log X, a term that arises from the configurational entropy of mixing. As a basis of comparison, the average molar Gibbs free energy prior to mixing, which we'll call G unmixed, is the molar average Gibbs free energy of the A and B before they are mixed, which is the mole fraction weighted average of Ga and Gb appearing in GIM. Thus, for mixing to occur spontaneously at fixed temperature and pressure, the RT X log X term must be negative so that GIM is less than G unmixed. To see if this is true, let's take a look at a plot of GIM versus XA. As you can see, GIM has a value of GB or GA at XA equals 0 or 1 respectively, corresponding to pure B or pure A. But at mole fractions in between, GIM drops below the Gibbs free energy of the pure species due to the random mixing term. To see this clearly, we can also plot G unmixed, which if we recast as an intercept and slope, is given by a tie line connecting GB and GA. So let's say we start out with unmixed A and B with overall system composition of 60% B and 40% A. Prior to mixing, the molar Gibbs free energy of the system is given by a point along the tie line at XA equals 0.4. After mixing randomly at fixed temperature and pressure, The molar Gibbs free energy is given by the point along GIM at XA equals 0.4. At this point, as well as any other composition we choose, the Gibbs free energy is lower in the mixed state than unmixed, so mixing is favored over separation into pure A and pure B. So what happens if the mixture is not ideal? As I mentioned earlier, let's consider the Margulis model, which adds an additional term to G equal to epsilon times XA XB, where epsilon is a parameter with units of energy per mole. One can think of this term as an additional free energy interaction between A and B molecules, which is proportional to the probability of A and B being adjacent to each other in a random mixture, which would be proportional to XA times XB. This term approaches zero for the pure compounds, and is maximum when the mixture is half A and half B. In most cases, epsilon is positive, thus representing an unfavorable increase in Gibbs free energy due to mixing. However, this positive energy is not a repulsion of A and B. It's a change in the Gibbs free energy due to replacement of more negative AA and BB interactions with somewhat less negative A and B interactions. Also, it's not clear from the formulation whether epsilon is a positive contribution to enthalpy, a negative contribution to entropy, or both. In fact, in many cases it will be both, since unfavorable energetic interactions between A and B tend to also make the mixing less random. In fact, as you'll learn more about in Chem E 326, energetic versus entropic effects often offset over the composition range being modeled, causing the Margulis model to be more accurate empirically than it should be theoretically. As shown here, in the limit of epsilon equals 0, the Margulis model just reduces to an ideal mixture. But if we increase epsilon to a value on the order of RT, it becomes significant, destabilizing the mixture relative to an ideal mixture. For epsilon over RT less than 2, G remains concave upward over its entire range, and thus still favors mixing. However, if epsilon over RT becomes greater than 2, interesting things start to happen. For example, here epsilon over RT equals 2.7. At first glance, we notice that G is still less than G unmixed. This is telling us that mixing is still favored over separation into pure A and pure B. But does that mean that the system will remain a single phase? For example, let's say that instead of separating into pure A and pure B, A and B form two different phases, alpha and beta, with the compositions shown here. What is the molar Gibbs free energy of the combined system? Recall that if we have two phases, we can express the overall intensive properties of the system as a weighted average of the intensive properties of the individual phases, where the weighting factor, F alpha, is the fraction of the total system moles that are in phase alpha versus phase beta. Applying this relationship to both Gibbs free energy as well as mole fraction, and then solving to eliminate F alpha, we see that Gibbs free energy will be a linear function of XA, given by a straight line connecting the points along G corresponding to phases alpha and beta. Thus, at an overall system composition of 0.4, the combined G of the two-phase system is lower than either unmixed A and B or fully mixed A and B. Thus, the lowest Gibbs free energy is achieved by two partially mixed phases of different composition. Note that in this case I chose the composition of alpha and beta. A and B are free to exchange between both phases, and will do so until the system reaches the minimum possible Gibbs free energy, consistent with an overall system composition of 0.4. This corresponds to lowering the tie line connecting alpha and beta as far as possible, with the endpoints someplace still on G versus XA. Reasoning from the geometry, this lowest possible position for the tie line corresponds to the cotangent of G versus XA. The endpoints of this lowest possible tie line are called the binodal points of G, and correspond to the two most stable phases that will form an equilibrium. As with any other tie line, these endpoints demark the edges of a two-phase region, within which any single-phase system will have a higher Gibbs free energy than a two-phase system of the same overall composition. An interesting phenomenon revealed by this plot is something called metastability. Magnifying the left portion of the graph and selecting a specific point near XA equals 0.4, we can see that the single phase is clearly higher in Gibbs free energy than a two-phase system of the same composition. Another way to say this is that the global change in system free energy is less than zero if the system splits into two phases. But how does it actually form two phases if it is initially one phase with a single composition? It must first separate into two phases of nearly the same composition, as illustrated here. For this to happen spontaneously, the local change in free energy must also be less than zero. Drawing in a tie line, we can see that this local change in free energy is also negative, so favors spontaneous phase separation. Another way to say this is that the concavity of G, given by the second derivative of G with respect to XA, is less than zero. In contrast, imagine a single-phase mixture in the two-phase region with composition near the binodal point. The change in global free energy upon forming two phases is clearly less than zero. However, near the binodal point, the concavity of G becomes positive. Thus, if we draw a tie line for two phases near this point, the local change in free energy upon phase separation is positive, which suppresses spontaneous nucleation of two phases. The transition between the two types of behavior described here occur at a point called the spinodal, defined as the inflection point along g of x, where the second derivative is zero. To the right of the spinodal, a single-phase liquid is clearly unstable and will spontaneously separate into two phases. Likewise, to the left of the binodal point, a single phase is clearly stable. But in between the binodal and the spinodal, a single phase will be metastable. This means that its Gibbs free energy is higher than the global minimum that the system could achieve by separating into two phases. So if it does phase separate, it will stay separated. But if it starts as a single phase and has no mechanism for phase separation, such as being seeded by a little bit of A-rich liquid or exposed to a surface with a preferential affinity for A, the positive second derivative of g of x prevents it from spontaneously separating. Expanding out to the rest of the diagram, we can summarize the unstable and metastable regions of the two-phase region, as shown here. Before applying these concepts to methanol and hexane, we need to address one outstanding issue, which is how to reconcile the minimization of free energy we've been discussing here with the generalized conditions of equilibrium, which, as we discussed in the last episode, imply that the chemical potential of species A must be the same in both phases at equilibrium, and likewise for species B. To see that these are really the same thing, recall from our discussion of the Gibbs-Duhem equation that we can always re-express G as a sum of the moles of each species times its partial molar Gibbs free energy in the mixture, which is also the chemical potential at fixed temperature and pressure. Dividing by the total number of moles, we can say that for the binary system here, the molar G of the system is XA mu A plus XB mu B. Taking the total derivative and then imposing the Gibbs-Duhem equation, as well as recognizing that dxB is minus dxa, we find that the total derivative of G versus XA is equal to the difference in chemical potential between A and B in the mixture. In other words, if we pick a specific point along g of x and draw a tangent, the local slope will be mu A minus mu B in the mixture. Combining with our original expression for G, this can be rearranged to show that the intercepts of the tangent at x equals 0 and x equal 1 correspond to the value of the chemical potential of A and B in the mixture, respectively, at this chosen point. This means that if we have two phases, alpha and beta, the chemical potential of A and B in each phase will be given by two sets of intercepts, as shown here. You can see that for the compositions I've chosen, alpha and beta are not in equilibrium, since mu of each component is not the same in both phases. So what will happen in this case? Since mu A beta is greater than mu A alpha, we expect species A to move from phase beta to phase alpha. Meanwhile, since mu B alpha is greater than mu B beta, we expect species B to move from phase alpha to phase beta. As this process occurs, the mole fraction XA in phase beta will decrease, while the mole fraction XA in phase alpha will increase. As this process occurs, the tangent intercepts will move toward each other, corresponding to the chemical potentials of A or B in each phase becoming closer to each other. This process will continue and continue and continue and continue until finally the chemical potentials of A in both phases is equal, and likewise for species B. This occurs at the cotangent, where the local slope of G versus XA is the same for both phases, in agreement with our previous analysis based on minimization of the overall Gibbs free energy. So these are really the same thing. Note that a common misconception is that Gibbs free energy is minimized when the compositions of each phase fall in a local minimum of G versus XA, where the slope of G versus XA is 0. You can see this is not true by drawing in the tangent at these 2 points, which shows that in this situation, mu A and mu B are both higher in phase alpha than in phase beta. So this is not a stable equilibrium state. You can also see this by drawing in a tie line between these 2 hypothetical phases. Although the decrease in G upon phase separation is negative, the cotangent, where mu A and mu B are the same in both phases, is slightly lower, so the system will continue to evolve until this global minimum is achieved. Okay, so the next thing we need to address is what happens to the boundaries of the 2-phase region as we change the temperature at fixed pressure, as we observed in the Pikachu diagram. One approximation we can try to make here is that epsilon is approximately independent of temperature. This would be the case, for example, if unfavorable interactions between A and B were mostly energetic and thus came from delta H of mixing, while the entropy of mixing remained the same due to random mixing. In this case, the dimensionless parameter epsilon over RT will decrease as temperature increases. Shown here, for example, is the case of epsilon equals 2.05. In this case, the binodal points approach each other, corresponding to narrowing of the 2-phase region. Repeating this plot over a range of epsilon over RT spanning 1.85 to 2.35, we see this narrowing ultimately leads to formation of a single phase for temperatures above a particular threshold. In order to calculate the boundary of the 2-phase region quantitatively, we need to convert our Gibbs free energy model into expressions for the chemical potential of A and B. Recall that for an ideal liquid mixture, mu A, which is the partial derivative of GIM with respect to Na, is G of pure A plus RT log XA. To predict the effects of non-ideal mixing, we must add the Margulis term to GIM. This is accomplished by multiplying epsilon XA XB by the total number of moles and converting XA and XB to Na and Nb, with the result shown here. Taking the partial derivative and simplifying, we see that the chemical potential will be higher than that of an ideal mixture by an amount proportional to epsilon times 1 minus XA squared. Applying to species B, we get something similar. So now imagine that we have 2 phases alpha and beta with different compositions, XA alpha and XA beta. Expressing the chemical potentials of A and B in both phases, and then requiring XA alpha equal XA beta and XB alpha equals XB beta, we end up with 2 equations in 2 unknowns, with one parameter, epsilon over R. Solving for XA alpha and XA beta as a function of epsilon over RT, we get the scaled Tx diagram shown here. This model predicts an upper critical solution temperature of epsilon over 2R, above which we only have a single phase. Below this upper consolute point, the system splits into 2 phases. I've drawn in tie lines for epsilon over RT equals 2.7 and 2.05, corresponding to the cases we examined earlier. Recall the example from episode A7 of a mixture of methanol and methylpentane, a 6-carbon alkane with molecular weight similar to hexane. At 20 degrees C, we observed that this mixture splits into 2 phases, a methanol-rich liquid, which segregates to the bottom of the container due to gravity, and an alkane-rich liquid. This mixture exhibits an upper critical solution temperature of 26 degrees C. Thus, when the mixture is heated to about 35 degrees C, which is above the critical solution temperature, the methanol and alkane become entirely miscible. Thinking in terms of molecular interactions, this implies that near 26C, thermal energy becomes just high enough to overcome the unfavorable interactions in the liquid, thus causing the free energy versus composition of the mixture to have a positive second derivative over the entire composition range. Based on the Margulis model, we can estimate the magnitude of the unfavorable interaction between methanol and methylpentane. Solving for epsilon and plugging in the measured upper critical solution temperature of about 300 Kelvin, epsilon is approximately 5 kilojoules per mole. This represents the net increase in free energy upon mixing methanol and alkane, relative to an ideal mixture. An interesting follow-up question is how the value of epsilon changes with the structure of the molecules. Generally speaking, interactions between molecules scale with the surface area of those molecules. Thus, we might expect unfavorable interactions to be stronger, and thus epsilon to be larger for larger molecular weight alkanes. Indeed, this is consistent with measurements of the upper critical solution temperatures of methanol-alkane mixtures, which increases with the molecular weight of the alkane. To illustrate this point, consider other 6-carbon alkanes having differing extents of branching, such as 2,3-dimethylbutane and N-hexane. Together, these three molecules span a range of branching from 0 branching, normal hexane, to 2 branches per molecule in dimethylbutane. We can also mix these alkanes in different ratios to obtain solutions with a non-integer average number of branches per molecule. Shown here are 3-to-1 solutions of these alkanes with methanol. At sufficiently high temperature, all of them form clear single-phase mixtures. Likewise, at sufficiently low temperature, all of them split into 2 phases. However, at intermediate temperatures, solutions with a critical solution temperature lower than the ambient temperature remain mixed, while solutions with a critical solution temperature higher than the ambient temperature phase separate. By varying the temperature and seeing at what point the various solutions phase separate, we can map out the upper critical solution temperature as a function of branching. This experiment shows a clear increase in upper critical solution temperature, and thus epsilon, with the decreasing branching, consistent with the higher surface area of the less branched alkanes. As an aside, we can also see that the rate at which phase separation occurs is slowest for solutions closest to the upper critical solution temperature. This suggests that the density of the 2 phases become more similar near the critical solution temperature. This is consistent with our scaled phase diagram, which shows that the composition of the 2 phases approach each other near the upper critical solution temperature. Given the unfavorable interaction between methanol and C6 alkanes in a liquid mixture, we might expect hexane and methanol to exhibit an azeotrope. Indeed, at 1 atmosphere pressure, a 50-50 mixture of N-hexane and methanol boils at about 50 degrees C, substantially below the boiling points of pure N-hexane or methanol, which are 68 and 64 degrees C respectively. Furthermore, as pressure is reduced, the temperature at which the mixture boils decreases, eventually dropping below the upper critical solution temperature and leading to a heteroazeotrope. At a half atmosphere, we get the behavior shown here. Some of you may recognize this as our friend Pikachu from episode A7. To take this one step further, let's try to apply the Margulis model to this mixture and see how well it explains the behavior in the phase diagram. Starting with the 2-phase liquid-liquid region, we get the results shown here, where the value of epsilon has been chosen to force agreement with a heteroazeotrope at T equals 32.7 degrees C. This model predicts that the upper critical solution temperature will be higher than the minimum boiling point of the mixture, so we can only calculate liquid-liquid equilibrium below 32.7 degrees C. The qualitative behavior of the model, including the narrowing of the 2-phase region with increasing temperature, is consistent with the phase diagram. However, the curvatures don't match, and the model predicts symmetric miscibility, which is inconsistent with a real 2-phase liquid mixture of methanol and hexane. Okay, so what about the gas phase? To understand this, we need to combine our model for chemical potential in the liquid with a model for chemical potential in the gas. As with the Clausius-Clapeyron equation, let's assume the gas phase is ideal, and thus obeys the ideal mixture approximation. As we derived previously, we can write the chemical potential in the gas as the Gibbs free energy of pure gaseous A at temperature T and reference pressure P0, plus RT times the log of the partial pressure divided by P0. Comparing to the expression we just used to model the liquid, we can see that they're based on a different secondary reference state. To resolve this, we can use the same trick we did deriving Raoult's law, which is to look in the limit of pure A, where the partial pressure of A becomes equal to the saturation pressure of A, and the chemical potential of A in the liquid becomes equal to the Gibbs free energy of pure A. Equating, we can relate GA in the gas at the reference pressure P0 to GA of the liquid. Substituting, we can eliminate the reference pressure and obtain an expression for μA gas which shares the same reference state as the liquid. Focusing first on liquid phase alpha, the resulting expressions for chemical potential in the gas and liquid are summarized here. At equilibrium, these two chemical potentials must be equal. Equating them and simplifying, we see that the reference state drops out of the problem, and we get an equation similar to Raoult's law relating XA alpha to XA gas with two parameters in it, epsilon over RT and the saturation pressure, which is also a function of temperature. Repeating for species B, we get a second equation with the same variables and parameters. We can calculate the saturation pressure for pure A and B using Antoine's equation. Meanwhile, we already have epsilon over R from the fit of the liquid-liquid equilibrium data. Thus, we have two equations in two unknowns and can solve for combinations of XA gas and XA alpha, which satisfy these constraints at a given temperature. I will post the spreadsheet showing this calculation on the course website, but the result is the two-phase liquid-vapor region shown here on the right side of the TX diagram. Applying this exact same formulation for liquid phase beta, we get another two-phase liquid-vapor region on the left side of the diagram. Comparing to the Uniquac model on which this phase diagram is based, you can see we have fairly good agreement, given that the Margulis model has only one constant parameter in it. Since this parameter represents the unfavorable interactions between A and B, it means that all the behavior we see here, including liquid-liquid separation and strong deviation from Raoult's law, all boils down to this unfavorable interaction. So there you have it. Pikachu, finally explained.